For this lesson, we're going to begin learning the basics for trigonometry. In order to get started, we need to learn a couple of definitions, and this first lesson is really a lot about those definitions and getting used to some basic terminology, as well as learning how to measure angles. And we're going to look at some common angles that you're going to see over and over again. So the first one is the definition of an angle. An angle is two rays that meet at the same point or have the same initial point. So a ray is an arrow that goes infinitely in any direction. So, but just one direction. A line goes infinitely in both directions. So this would be a ray. And then I make another ray that has the same initial point. The initial point being the starting point. So this is my initial point. Okay. Now the measure of an angle is the amount of rotation required to rotate one side, which is we're going to call the initial side, to the other side called the terminal side. So if I take one side here and I consider this side or this ray to be my starting side, or that's going to be my initial side. Okay. The amount of rotation it takes to get to the other ray, this one here, which we're going to consider to be the terminal side, is the measure of the angle. Now there's different ways to measure that rotation, but the measure of that rotation is the measure of the angle. This initial point that these two rays share, we're going to consider to be the vertex. So this point right here is my vertex. And this right here, what I drew, is an angle just sort of floating off in space. Largely what we're going to look at are angles in standard position. And an angle in standard position is an angle that its vertex is at the origin 0, 0, and their initial side is the positive x-axis. So if I have the xy plane here, here's the x-axis, here's the y-axis. If I'm going to draw an angle in standard position, the initial side is going to have its vertex at 0, 0, and the initial side is going to be the positive x-axis. And then I'm going to rotate from there to get to the terminal side. Well, I could rotate it this way, or I could rotate this way. If I rotate counterclockwise, this angle that I created when I go counterclockwise will be measured in a positive value. If I go counterclockwise, if I go clockwise, this way, the measure of that angle will be measured with a negative value. So if I end up, say, here, from doing it this way, I'd end up with a negative value. So when you see an angle that has a positive or a negative value to it, all that it's saying is which way you rotated to get to the terminal side. Did I rotate counterclockwise or clockwise? And it's kind of counterintuitive to what you think should happen. You would think if I'm going clockwise, that would be positive, but it's not. We measure counterclockwise as a positive and clockwise as a negative. We label these angles in different ways. With the two common ways you can label an angle is either with the Greek letters alpha, beta, theta. So we can say this angle right here is alpha, and this angle right here we can call beta. And that's if we're trying to refer to multiple angles. You know, you have different names for them. So I can say this angle, alpha, beta, or this one, theta. And then you know what angle I'm talking about. And that's typically the way we label angles. But you can also label them using our standard alphanumeric letters. So we could say A, B, C. This angle is angle A. This angle right here is angle B, which is very similar to beta. But if we're going to do this, we're going to use capital letters. Okay? Because we use lowercase letters to denote lengths of sides of these angles. But we use capital letters to denote the actual angle themselves. So it's two different ways to do it. Now, if I'm looking at a picture, let's say here, let me erase this. If I'm looking at this picture here, okay, I have two angles that I kind of created here with these two rays. This is one angle that goes here, and that will be measured in a positive value. it starts in standard position on the positive x-axis and then goes into the second quadrant. And that's where the terminal side is. Okay? But there's also another angle I've created too, which is the angle that goes the opposite way, but still ends in the same spot. So it starts in the same spot and ends in the same spot. I just got there a different way. I got there by going clockwise instead of counterclockwise, which would be the negative angle. So if I call that angle, say, beta. These two angles are related in that we call them coterminal angles. Okay? Coterminal angles are angles that are in standard position that have the same terminal side. So essentially what it means is they start and end in the same spot. So these two angles, alpha and beta, are coterminal. Even though I got to where I was ending up at in a different way, I still ended in the same spot. Another angle that's coterminal to these two would be, say, an angle that starts in standard position, rotates around all the way around once, and then keeps going, and then eventually ends right here. So it ends right here again. That angle, which we'll call, I don't know, theta, that's also coterminal to the other two. I mean, I could go around 50 times. And then if I end up, say, right here, okay, whatever angle that is, the measure of that will be coterminal to all these other ones, okay, because they all start and end in the same spot. And that's going to be a pretty important thing throughout trigonometry, is the relationship between coterminal angles and some of the trigonometric functions. So as I said a second ago, the measure of an angle is determined by the amount of rotation from the initial side to the terminal side. Now we can measure that rotation in two primary ways, in degrees and in radians. So we'll look at degrees first. So the definition of a degree. The definition of a degree is the amount of rotation in an angle with the measure of 1 degree denoted by this 1 degree, this little symbol right here is your degree symbol, is equivalent to the rotation of 1/360th of an entire circle. So the definition of a degree, a single degree, is to just take a circle, cut it up into 360 equal parts, and each piece would be what we consider to be 1 degree. So, you know, if I take a circle like this and I just cut it up into 360 equal parts, I just keep cutting and cutting and cutting, so eventually what I have is, you know, all these slices like this, and each one of these little slices, and this is a pretty terrible picture, each one of these slices here, the measure would be 1 degree. So it's just 1/360th of a full rotation. Okay, so if I start in, say, standard position here, and I go full rotation around, 1/360th of that full rotation is what 1 degree is. Now, let me erase this mess so I can get it a little bit neater. So if I'm looking this, say, in the XY axis, here's the x-axis, here's the y-axis, and I'm starting in standard position. Well, a full rotation all the way around, an angle that starts here, you know, and goes all the way around and ends right there, would be 360 degrees. Which I think most people understand some very basic degree measurement just from living in the real world. But then we have, you know, what would half a rotation be? What would a quarter of a rotation be? Well, once you know what a full rotation is, 360 degrees, because, you know, basically what we're doing is taking a full rotation and cut it into 360 parts. You stack all those parts together, there's 360 of them, and that's where you get the 360 degrees. If we know what a full rotation is, then what we can do is, okay, then just cut that in half, and that's what half of a rotation would be. So half of a rotation, okay, which would start in standard position and would end right here, okay, that should be half of 360, or 180 degrees. Right, then I can go, okay, quarter of a rotation, so starting in standard position and then going here, that would be quarter of a rotation, so my terminal side is the positive y-axis. That's a quarter of 360, so if I take 360 and I divide it by 4, I would get 90, so it's 90 degrees, and I can just keep going from there. there's going to be a set of common angles you're going to see. And the common angles are going to be angles that are going to come up over and over and over again. So these common angles are 30 degrees, 45 degrees, and 60 degrees. And then we're going to basically look at multiples of those. So if we look at where these things would fall, let's just say, let's look at the first quadrant. Here's the x-axis, here's the y-axis, here's your origin 0, 0. Okay. So we would have a measure where we start in standard position and we don't move anywhere. That would be 0 degrees. 30 degrees would be this measure here, is 30 degrees. If I split that first quadrant completely in half, this measurement would be 45 degrees. If I go 60 degrees rotation here, so sorry, this is 60 degrees, and then a quarter rotation around the circle, which would put me on the positive y-axis. That would be 90 degrees. Okay, so these are your common angles you're going to see. And then what I'm going to do is I'm going to put those around the xy plane, so then multiples of those angles. So multiples of 30 or 60, you know, we could have, say, 120. 120 degrees would be here. Right, that would be 120 degrees. Another multiple would be 45 degrees times 2 is 90, times 3 puts me right here at 135 degrees. Right, and that's where 135 degrees would fall. And then if I do 30 times 1, or 30 times 2 would be 60 degrees, 30 times 3 would be 90 degrees, 30 times 4 is 120 degrees, 30 times 5 is 150 degrees, which puts me right here. So that angle would be 150 degrees, and then we also have 180 degrees is halfway around the circle. So that would put me on the negative x-axis, so that's my 180 degrees. Okay? But again, multiples of these three angles are going to be your common ones, so sort of seeing how they fall in the first quadrant is going to be important. And then we're going to look at multiples of that as we move our way all around the xy plane. Okay? Another way to measure angles is in radians, and this is more useful usually in most branches of calculus, or even in just most branches of mathematics, and it has to do with the unit of measurement. When we look at a degree and we write something in degree measure, we use a symbol. We use the little degree symbol. And I would write it as, 1 degree, okay, or 26 degrees. And that little symbol is the unit of measurement for degrees. Radians, on the other hand, doesn't quite have that unit of measurement, which is actually more useful. And I'll explain that in a second. But radians is another method of measuring a rotation of an angle. So we look at it, and in terms of the definition, okay, we look at the central angle of a circle. And the central angle of a circle is essentially an angle that rotates around the circle. So if we look at the definition of a radian, it's the measure of the central angle, say theta, that intercepts an arc S equal to the length to the radius r of the circle. Now that probably makes no sense, right? And that's fine. If I draw a little picture, I think it'll make more sense to you. The idea is this. I take a circle, okay, and I look at some angle inside that circle. So let's just say we have this angle here that goes around like this. This is my angle theta. That's what we call the central angle. That angle intercepts an arc S. Well, the distance traveled around the outside of the circle is what we call the arc length. And that is what S is. Okay? So this angle intercepts an arc length S equal to the length of the radius r of the circle, would be the measure of 1 radian. Well, this distance right here is r. That's the radius of the circle. This is also r, right? When you have a circle, the radius is the same all the way around. When this distance is equal to this distance, this angle will be equal to 1 radian. Now you might say, well, that means for different circles, 1 radian would be different. In that, you know, if I have a bigger circle, so I have a bigger radius, and if I have a bigger radius, it should take longer to sweep around that distance. Well, no, actually, all circles are proportionate to one another. So whether I have a little circle or a big circle, this distance here is proportionate to this distance here. So no matter what circle you have, 1 radian measure, this rotation will always be the same no matter how big the radius is, because as the radius gets bigger, the distance I have to travel also gets bigger, the arc length, and when those two are equal, that's when I'll have 1 radian. Okay? So if that's the case, then we have sort of a formula we can use to create radians. And this formula right here is that the angle, if measured in radians, can be calculated by doing S over R. S being the arc length, and R being the radius. And this is a very different concept than degrees. In degrees, we just take a circle, cut it into 360 equal pieces, and each one is just a degree. This is looking at the relationship between two distances and using those two distances to calculate the measure of 1 radian. Now, why is this formula going to work? Well, because think about it. If my angle has to be 1 radian, it's when this measurement and this measurement are equal. Well, if I have the same thing over itself, I would get 1. So this formula is a legitimate formula. And think about it. If I have an angle smaller than 1 radian, so let's say I have an angle that's here. Okay, so this is my angle. That would be smaller than what I consider to be 1 radian. The radius is still the same, but the distance I traveled is smaller. So the arc length is now smaller than what it was before. So instead of these two things being the same and I'm getting 1 radian, I want to get a measure smaller than 1 radian, because you can clearly see that this smaller black angle is definitely smaller than the bigger red angle. So the measure should be smaller. Well, if this distance is smaller than this distance, which clearly it is, the numerator of this fraction is smaller than the denominator of that fraction, which means that the whole fraction's value should be smaller than 1. Whenever your numerator is smaller than your denominator, you would always get an answer to the whole fraction to be smaller than 1, and therefore I would get an answer for this angle smaller than 1 radian. And conversely, if I travel further this way, so if I went all the way this way, right? My radius is still the same, but the distance I traveled is now bigger than what it was before. Well, if this S, right, is bigger than this R, in terms of just fractions, when your numerator is bigger than your denominator, you get a number bigger than 1. So the measure of this angle would be bigger than 1. So this formula is the legitimate formula for calculating radians, just based off of the intuition of how fractions work. Okay? So the definition of a radian is important. The idea of how it's different from the measure of a degree is important. And also now sort of the key of why radians are helpful throughout mathematics. Well, degrees again have a unit of measurement. 1 degree or 25 degrees. This is the unit of measurement. Where radians is not really a unit of measurement, almost as if it's like a unitless unit of measurement. Now, that's not quite right, but it's a changing unit of measurement in that if I'm just dividing these two distances, however I calculate those distances is essentially the units of measurement I'm using to create my angle. So this is a distance, this is a distance, and I'm dividing those distances to calculate this angle. So if I measure radius and arc length in inches or feet or meters, then that's sort of changing the units in which I'm calculating my angle. So in a way, we consider these radians to really not have a unit of measurement, which is important because if it's not a unit of measurement per se, we can just call it units, And if it's just units, we can compare it to other units, which compares better in the xy plane. Whereas if something has a unit of measurement like degrees, you can't compare it to something else unless that something else has the same unit of measurement. It's the idea of if you're trying to calculate and or compare inches and liters. It's not very easy to compare inches and liters because inches and liters are two completely different units of measurement. And 1 inch and 1 liter, just because they're both 1, are not necessarily the same. Whereas, if you're trying to compare 1 unit in this field and 1 unit in another field, if they're just both 1 unit, then you can compare those two numbers together and say, okay, those are the same numbers or one number's bigger. But if they're two different units of measurement, just because one's the same or one's bigger or smaller means nothing. Okay, 5 inches and 1 liter. Just because 5 inches is a bigger number doesn't mean it's bigger in overall value than 1 liter is. It all depends on what you're looking at, and you can't really compare those. So that's the nice thing about radians, is we think of it like it's a unitless version of measurement, or essentially the unit of measurement for radians is just units. We call it radians, but it's like units, whereas degrees has a specific unit of measurement, and that is degrees. So now we need to look at some common radian measures. Okay, we know how we came up with a radian, but now we got to look at some common radian measures. So a lot of this has to do with the circumference of a circle, sort of the same method we used for degrees. We looked at what a full rotation in degrees was, and then we just cut that full rotation in half and figured out what half a rotation's measure would be, and so on. Well, this is the same idea. We got to look at what a full rotation around the circle would be. Well, if you think about a full rotation around the circle, right? If I went all the way around the circle, this is my radius of my circle. The distance traveled all the way around the circle is called circumference. And the formula for circumference is 2 pi r. Okay? So if I'm going here and I'm traveling all the way around, that distance I traveled all the way around we call circumference. But really what it is arc length too. This is the same thing as s. So if I'm trying to figure out what this angle is that is a full rotation in radians, I should take s over r. Well, this is the arc length that I traveled around the circle, and the radius of the circle was just r. I cancel these r's and I get 2 pi. So the measure of this angle in radians would be 2 pi. So a full rotation around the circle would be 2 pi. So then I start to say, okay, well then what would half of a rotation be around the circle? So if I went halfway around the circle, what would that measure be? So what would that angle, say beta, be? Well, if I take my full rotation and I divide it in half, the 2's would cancel and I would just get pi. So half of a rotation around the circle is pi radians. A quarter way around the circle, so if I start here and I go only a quarter of the way around the circle, it should be the full rotation, which is 2 pi divided by 4 because it's a quarter. Simplify, I get pi halves. So pi halves is a quarter rotation. I could do a sixth of a rotation. I can do, a 12th of a rotation. I mean, anything you can do. So you start to look at, say, a sixth of a rotation. Full rotation is 2 pi. A sixth of that would be pi thirds, because 2 over 6 simplifies to 1 over 3. So pi thirds radians would be a sixth of a rotation. Again, when we're writing radian measures, we could either just write radians or just not put units at all. So if you see an angle, and you see an angle written like this, theta equals 26 degrees, then you know that's measured in degrees. But if I see theta equals, say, 26, then because you don't see the little degree symbol and there is no units given for that angle, you assume that that angle is measured in radians. Even though maybe you didn't write radians next to it, if you don't see the angle, assume that it's in radians. So, something like this, if I see an angle as 2, then that's 2 radians. Now, some of our common ones that like we just looked at, half a rotation, quarter rotation, the angle is a multiple of pi. So 2 pi, pi over 2, pi over 3, because these are some common ones. But every angle in radians doesn't have to have a pi in it. You could have an angle in radians be 26. Now, one thing I see lots of times with students is they see the difference between radians and degrees, but they don't know how they compare. Like, what does 1 degree look like compared to what does 1 radian look like? Well, 1 degree and 1 radian are very, very different. So if we look at this circle, if I go all the way around the circle, if I travel all the way around the circle, full rotation, we said the angle was 2 pi. And the circumference is 2 pi r. Okay? But the angle itself is 2 pi. So if I want to figure out how many radians that is, that's 2 pi radians, right? That's the measure in radians. The angle is 2 pi radians. Well, 2 pi is 2 times roughly 3.14. And that's what we think of pi to be, 3.14. So an estimate, right, this is really kind of an estimate, for this angle would be 2 times 3.14 or 6.28. So a full rotation all the way around the circle is roughly 6.28 radians. So if I stack 1 radian on top of 1 radian on top of 1 radian as I go around this circle, it will roughly be 6.28 radians. So 1 radian, 2 radians, 3 radians, 4 radians, 5 radians, 6 radians, and then 0.28 of a radian, so a smaller piece of a radian, would get me all the way around the circle. Whereas if I'm doing degrees, and I'm going all the way around the circle, and I stack 1 degree on top of 1 degree on top of 1 degree, I have to have 360 of these to get all the way around the circle. So 6.28 radians and 360 degrees gets me all the way around the circle. So clearly 1 radian is far bigger than 1 degree is. Okay? And that's something you got to understand, is that when you're looking at the difference between ways of measuring an angle, degrees versus radians, you got to look at the different sizes of those angles. So this picture kind of demonstrates the relationship between all these special angles. So we talked about how if you look in the first quadrant, you have your 0, 30, 45, 60, and 90 degrees. Okay? And that's what this would be. This would be like your x-axis here. And this is your y-axis here. But you also see what those corresponding angles are in degrees as well. So you got pi sixth, radians, pi fourths, radians, pi thirds, radians. And pi sixth is the same thing as 30 degrees, pi fourths radians is the same thing as 45 degrees, pi thirds, same as 60 degrees. And you need to make yourself familiar with these particular angles and where they fall, both in radians and degrees. So we have 90 degrees and pi halves. You keep going around, 2 pi thirds and 120 degrees. And if you look at it, 60 degrees and pi thirds are the same. 120 is 2 times 60. Well, 2 times pi thirds is 2 pi thirds. So the idea is that this angle right here is a multiple of this angle here. And you keep going, 45 degrees. 3 times 45 degrees is your 135 degrees. So this is a multiple of 45. And 3 times pi fourths, which is also the same thing as 45 degrees, 3 times pi fourths is the same as 135 degrees. So you're going to have to keep, again, recognizing where these angles fall, because these are what we call the special angles, and these angles we're going to refer to over and over and over again. 150 degrees, 5 pi sixth. We go halfway around the circle. In degrees, that's 180 degrees. In radians, it's pi radians. Quadrant 3, a multiple of 30 degrees, right? If we do 7 times 30 degrees, we get 210. And 7 times pi 6 is 7 pi 6. Pi 6 and 30 being the same. 225 is a multiple of 45, as well as 5 pi fourths is a multiple of pi fourths. I think it's much easier to look at radians in terms of the multiples than it is in degrees. Like, you clearly see that this is a multiple of pi thirds, and this is a multiple of pi fourths, and this is a multiple of pi sixths. So you know what angle these came from. They were all multiples of pi 6, pi fourths, and pi thirds. So as you're going through the homework or as you're just working with these things, you're going to become more and more familiar with the angle measurement in both radians and degrees. Okay? And I think the degrees one most people have down just from general knowledge, 0, 90, 180, 360, but you really probably going to have to focus more on the radian measure because that's probably something you haven't seen a whole lot before. And it's actually something we're going to use most. We're going to use radian measure more than we use degree measure. So now we need to pick up with a couple more definitions. Alright, acute angles. Acute angles are all angles that have measure between 0 degrees and 90 degrees. Okay? If my angle measure is between 0 and 90 degrees, then it's considered to be acute. In radians, that angle would be between 0 radians and pi halves radians. Okay? So this angle theta, this is the symbol I just wrote here, is theta is my angle between 0 degrees and 90 degrees, or 0 radians, pi halves radians. If you look, when I do degrees, I use the degree symbol. When I use radians, I don't write any notation other than the number itself. Obtuse angles. Obtuse angles are between 90 degrees and 180 degrees. Or in radians, that obtuse angle, say beta, would be between pi halves radians and pi radians. Okay? So this is just a definition of acute and obtuse. Another definition that's important we already talked about is the idea of coterminal angles. Coterminal angles have the same initial and terminal side. They start and end in the same spot. So we talked about this. If I have an angle like this angle right here, say theta, is coterminal to this angle here, say beta. Okay? They both start and end in the same spot. So if I want to find some coterminal angles for the following, let's say for theta equals 37 degrees. Okay? If theta equaled 37 degrees, I want to find a coterminal angle for that. And sometimes the question will be worded like, find two coterminal angles, one positive and one negative, for a corresponding angle. So what I have to do is find another angle that ends in the same spot. So here, if I said, alright, here's 37 degrees right here, I could find this other angle that goes this way, or what I could do is I could just rotate from here another full rotation and end up back there again. So the way you do this is essentially you either add or subtract a full rotation from your angle and you'll end up in the same spot. Well, in degrees, a full rotation would be 360 degrees. So coterminal angles would be 37 degrees plus 360 degrees, or 37 degrees minus 360 degrees. Either of those angles that I get from that would be coterminal to 37. So if I do that computation, I get 397 degrees, or if I do the computation for the other one, I get negative 323 degrees. And these two angles here are coterminal to 37. They end at the same location. 397 degrees would be this angle that goes around like this and comes back and goes there. It's more than 360, and it's 37 degrees more than 360, so it's a full rotation plus another 37 degrees. Negative 323 would be the angle that starts here and rotates back this way and ends here. But they all start and end in the same spot. 37, 397, negative 323. Now if I want to do this in radians, I could say find, coterminal angle to, say, beta equals pi fifths. Alright, so if I want to do, say, pi fifths, well, what do I have to do? I have to add and subtract a full rotation, but in radians, that's 2 pi. So, coterminal, I would say pi fifths plus a full rotation, in this case, 2 pi. Whatever that is would be coterminal. I could either add or subtract, too. Another coterminal one would be pi fifths minus 2 pi. Now the problem with this is it's a little bit harder, the computation, because you got to deal with fractions lots of times, and when you're dealing with fractions you got to do common denominators. So here I'd get pi fifths plus this one. If I multiply by 5 over 5, I get 10 pi fifths. That's really 2 pi, so that gives me 11 pi fifths. Okay. I do the same thing for the other one. I have pi fifths minus 10 pi fifths, so that gives me negative 9 pi fifths. But still, these two angles are coterminal to this angle. They both end in the same spot this one's. They start and end in the same place. In certain situations, it may be convenient to convert a radian measure to a degree measure or vice versa. So you can convert back and forth between radians and degrees, and it's simply by multiplying by pi over 180 or 180 over pi. If you're trying to convert from degrees to radians, so you're starting in degrees and you're going to radians, simply multiply by pi over 180. And the reason for this is to look at the relationship between radians and degrees, and the fact that pi and 180 are equal to one another, so you're converting to one unit essentially of measurement. And really what this is really multiplying by 1, but it's multiplying by a form of 1 that's going to cancel out your old measurement and give you a new measurement. Radians to degrees, you start with radians, you end up with degrees. If you want that to happen, you multiply by 180 over pi. And the easiest way to remember which one it is you got to figure out, well, which unit of measurement do I want to cancel and which one do I want to be left with. Pi you think of as the radian, and the 180 obviously, because the symbol is the degrees. So I'm starting with 135 degrees and I want to convert that to radians. So what I'm going to do is I'm going to multiply by something that has degrees in the denominator, so that degrees will cancel. Well, that's the 180 is going to have to go in the denominator now, so pi will be in the numerator. So now what happens is my degrees will cancel and I'm left with radians, which is what I want to be left with. So I get 135 pi over 180. If I simplify that, I end up with 45 goes into both of those. 45 goes into this 3 times, goes in 184 times, so 3 pi fourths. If I want to do the other way, I want to have pi fifths, which is a radian measure, and I want to convert that to degrees. Well, I want radians to cancel, so I want radians in the denominator so that my radians will cancel, which tells me pi has to be in the denominator. The 180 goes on the top, so I'm left with the degrees. So then I end up with 180 over 5 degrees, right? So what happens here, I simplify this. Well, 5 goes into 180. What's that going to be? So it'll be 36 times. Alright, so usually you probably wouldn't write the answer like that. I would try to say you write the answer as 36 degrees. I went from radians and I'm left with degrees. There are a bunch of applications of trigonometry. Now, we haven't done a whole lot of trigonometry. We've just dealt with some terminology with trigonometry and the idea of angles. But we can do at least a couple of different applications, and one would be arc length. So if I'm trying to calculate the arc length of something, well, the idea is this, right? I have a circle, right? I look at some angle around that circle. That circle has a radius. This distance right here is arc length. We label that S. If I'm trying to calculate the arc length, from here to here. Obviously, you could measure it, but you'd have to have a bendy tape measure or something to do that. Calculate it, computationally, we have to have a formula for that. Well, we have this formula, theta equals s over r. And that was a formula for radians, right? That was how we came up with radians. S is the arc length, r is the radius, and the angle is measured by the ratio of the arc length to the radius. Well, since that's a formula that has s in it, we can use that to help us find s. We can solve for s and get s equals r over theta. And this is a formula we can use to find s. Now the problem is, you need two things. R, which is the radius of the circle, and theta. But theta must be in radians, because this came from the radian formula, right? This is a measure of radians. So the angle, since it came from that formula, has to be in radians. If it's in degrees, you have to convert to radians first. But other than that, this is just the formula you need. So I have a circle, and that circle has a radius of 4 inches. I want to find the length of the arc intercepted by the central angle, 240 degrees. Which is basically saying if this angle right here was 240 degrees, which that's not accurately drawn, but if I have an angle of 240 degrees and a radius of 4 inches, I need to calculate the arc length. So I use this s equals r times theta. What I can't do is say 4 times 240 degrees. That won't work because that angle is not in radians. So what I first have to do is take theta of 240 degrees and convert it to radians. So that's going to be pi over 180. I simplify, the zeros will cancel. 24 over 18, 6 goes into each, so 4 pi over 3 is my radian measure. So then I say, okay, my arc length is r times theta. R was 4. This is 4 pi over 3 is my angle, so I get 16 pi over 3. Now this is a length, right? Arc length is a distance, it's a length, so what's the unit of measurement we're going to use? Well, since the radius was measured in inches, I should measure this distance in inches as well, so inches. So that would be a fairly simple application of some things you can do. Measuring arc length, measuring angles, measuring radius, in this case arc length. To begin talking about the sine and the cosine function, we need to look at the unit circle. This picture that you're seeing here is a picture of the unit circle. The unit circle is a circle that's centered at the origin, so this point right here is at 0, 0 on the origin for the xy axis, and this being the x-axis, this being the y-axis. So it's centered at 0, 0 on the xy axis, and it has a radius of 1. The equation of that circle is this equation right here. X squared plus y squared equals 1. Now you may not be familiar with equations of circles, but an equation of a circle has this form. X squared plus y squared equals r squared, where the center of this circle would always be at 0, 0, but the radius of the circle changes depending on what r is. Okay? So r squared, this number right here is r squared. In this case, that's 1 squared is 1, so the radius is 1. We're primarily going to stick to this unit circle to start, but then eventually we're going to start looking at any circle with any radius. Alright, so with this unit circle, right, you should be familiar now with the angles inside the circle. This was the purpose of the last lesson, was to get you familiar with the fact that there are common angles, 30 degrees, 45 degrees, 60 degrees, 90 degrees. Okay? And in radians it would be pi sixths, pi fourths, pi thirds, pi halves. And when we look at these common angles, then we can take multiples of those common angles and start working our way around the circle. So we have 120 or 2 pi thirds, 135, 3 pi fourths, and so on. And at this point you should be familiar with what angles fall where. If I said 30 degrees, you know it falls in quadrant 1. If I said 210 degrees, you know it falls in quadrant 3. If I say 11 pi 6, you know it falls in quadrant 4. So this is what you're going to have in your knowledge to be able to move forward. Now what we're going to have to start looking at is the idea of these points that are associated with the unit circle. Okay? Because these points that are associated with the unit circle, this point here, square root of 3 over 2, comma 1 over 2, and so on, are the points we're going to use to help us evaluate what we're going to call the sine and the cosine function. And this is fairly intimidating when you look at it at first, but there's a pattern to how this whole thing develops, and as long as you have the angles inside down at this point, then you should be able to do the points around the outside. Now if you still are having trouble with the angles inside the circle, there's a little trick that you can use to help you remember some of this. Like if I said, where's 11 pi sixth? Right, so 11 pi sixth is here. What I would do is I would relate 11 pi sixths to a whole number multiple of sixths. So in that case what I'm saying is you would look at, say, 12 pi sixths. Okay? 12 pi 6 would simplify to a whole number, right? Because 12 over 6 is 2, and this is actually 2 pi. So if I know where 2 pi is, and everyone should know at least where 2 pi is, then 11 pi 6 comparable to 12 pi 6, or 2 pi, is smaller. So if 11 pi 6 is a little smaller than 2 pi, or 12 pi 6, that puts me, here's 2 pi is right here, a full rotation, so I should just back it up a pi 6, and that's where 11 pi 6 will fall. If I go, say, 7 pi 6, and I want to figure out, okay, where's 7 pi 6? I can't remember where that falls. Well, I try to think of what's a whole number that I can work with that's really close to 7 pi 6. That would be 6 pi 6. So 6 pi 6 is the same thing as pi, and I know where pi is. 6 pi 6 and pi are the same, and I know that pi is right here. So if I want to try and find where 7 pi 6 is, well, 7 pi 6 is bigger than 6 pi 6. Well, how much bigger? A pi 6 bigger. So if I know where pi is, and I have to just go a pi 6 further around the circle from that, like I'm traveling this way, I go to pi, I got to go another pi 6 further than that, that puts me right here. So that's sort of the easy way to remember these things. Or let's say 5 pi 6, right? I'll take 5 pi 6 and relate it to 6 pi 6 as well, but that's a little bit smaller. So I have this like 6 pi 6, which is pi, I have 7 pi 6, and I have 5 pi 6. So I go, okay, well 7 pi 6 is bigger, 5 pi 6 is smaller. So if I know 6 pi 6 is right here, then I'll go back a little bit to get 5 pi 6 and forward a little bit to get 7 pi 6. And that can tell me kind of where these angles fall, and I think that's the quick way to kind of remember where these are if you still are having trouble remembering where each one of these special angles falls. Alright, so now that we have this picture, we're going to have to start learning about these points on the outside. Alright, so here's what we need to learn about when it comes to these functions. There are two functions that we're going to learn about in this lesson, and they're the sine and the cosine function. Altogether there are 6 trigonometric functions, but we start off only learning about 2, because these 2 trigonometric functions are the basis for all the other ones. So we're going to learn about the sine function, okay, the sine function, the sine of theta. We abbreviate the sine of theta using sin parentheses theta, and here we're taking the sine of an angle. Okay, we also have the cosine of theta that we're going to learn about, and we abbreviate that cos parentheses theta, and that's the cosine of theta, the cosine of this angle. So these trigonometric functions are functions of an angle. Okay, functions of theta, beta, alpha, whatever angle you're dealing with. So you have the cosine of theta and the sine of theta. Now we define these in this way. If theta is an angle in standard position, and xy is a point in the intersection of the terminal side of the unit circle, then the sine of theta equals the y coordinate of that intersection, and the cosine of theta equals the x coordinate of that intersection. So here's the idea, right? We're looking at, say, a unit circle. I just sort of blew up the first quadrant here. So I have this first quadrant. This is my y-axis. This is my x-axis. Here's the unit circle. I'm going to take some angle in that unit circle. So here's my angle, theta. That angle's terminal side, which is right here, because it's in standard position, right? The key is that part of the definition says standard position. If my angle's in standard position, the terminal side of that angle will intersect the circle somewhere. And it will intersect the circle at a point. It depends on how far I rotate as to which point I intersect, but it will intersect the circle at a point. Okay? That point should have an x-coordinate and a y-coordinate. So we're going to define the sine of theta. Okay? The sine of this angle will be defined by looking at the y-coordinate of this intersection point. And the cosine of theta will be defined as the x-coordinate of this intersection point. So we're relating basically what these two functions do. If you think of them as a function, right, that goes from here to here, what they do is they match an angle theta with either a y-coordinate, that would be for the sine of theta function, or they match an angle with an x-coordinate, and that would be for the cosine of theta function. Okay? And that's how these functions work. Like you have certain functions that we've already learned about, like the squaring function. What do? They match a number with the square of that number. Well, these functions match an angle with an x or y coordinate based off of an intersection point with this angle's terminal side and the unit circle. So if you know the intersection point for certain angles, then you know what your answers are going to be for given angles. And that's sort of what we need to learn, is we need to get used to these intersection points. So if I start to look at this here and I say, all right, well, here is the first quadrant of the unit circle, and we're going to have to get used to learning these points. Okay. Well, if I start to look at these points, I say, okay, well, what's the sine of 30 degrees? And it doesn't matter whether you do degrees or radians, because it's the same angle, just depends on how you want to measure it. If I want to do the sine of 30 degrees, if I know where 30 degrees is in the unit circle, it's right here. Here's my angle, theta, it's 30 degrees. If I know the intersection point for the terminal side on the unit circle, this is it right here, then I can find the sine of 30 degrees by primarily just looking at the y-coordinate. The y-coordinate's a half, so the sine of 30 degrees is a half. If I want to find the cosine of 30 degrees, okay, I have to look at the x-coordinate for that intersection point. That's square root of 3 over 2. So the cosine of 30 degrees is square root of 3 over 2. If I did it with radians, it's the same thing. The cosine of pi 6, which is also the same thing as 30 degrees, is square root of 3 over 2. Because that's the same intersection point. I just measured the angle with radians instead of degrees. So if I know these intersection points here, here, and here, I can find the sine and cosine of these angles. And that goes for all the special angles around here. Now, if it's some angle like, I don't know, an angle that falls here, say 72 degrees, right? 72 degrees would fall right there. In order to find the sine or the cosine of 72 degrees, I need to know this intersection point. Well, that's not as easy because I can't remember all the intersection points for every single angle in the unit circle. It's impossible. What we do is we get used to the ones that come up most often, our special angles, and we get used to these. And then eventually, if we know these, we can then use that to help us find other angles. Well, maybe not 72 degrees, but at least some other angles that maybe we can combine these multiple angles to get another angle. So we'll get to that. That's farther, way farther down the road. But right now we need to get used to these. So one thing you're going to see, if you're going to be looking at the x-coordinates and the y-coordinates for your cosine and sine function, then we're looking at domain. Well, domain for each function, any function, and all the values that you can plug in this case theta. Theta would be my domain values. Well, as long as I can take an angle, so I have, say, sine of theta, as long as I can take some angle and plug it in and get an answer, then it will be in my domain. Well, no matter what angle I look at around the unit circle, that angle is always going to intersect the unit circle, okay? And it's always going to have a y-coordinate. So every angle I use when I take the sine of it, I will always have an answer for. Now, what the answer is isn't that easy to find, but you'll always have an answer for it. Well, if that's the case, that means I can let theta be anything, any angle around the circle. in any rotation, positive, negative, doesn't matter, will always give me an answer. If that's the case, then the domain for the sine function should be all real numbers, negative infinity to positive infinity. Same thing for cosine, because you'll always get an x-coordinate as well. So the domain for cosine is all real numbers, or negative infinity to positive infinity, which means you can take anything and plug it into the sine or the cosine. Now the range, however, which are the answers that come out, in this case for the sine are the y-coordinates, and for the cosine it's the x-coordinates, will be negative 1 to 1. Because if I go back to my unit circle, full unit circle picture, if I'm looking at all the x's and y coordinates in this unit circle, the biggest y coordinate I'll ever get is 1, and the smallest y coordinate I'll ever get is negative 1, and whether the angle's in this side or this side, I'll have y values between negative 1 and 1. Okay? So all my answers will always be between negative 1 and 1 when it comes to the y coordinates, which comes to sine. So that means the range, or the answers I'm getting out of the sine function, are between negative 1 and 1. Same thing goes for cosine. The biggest x value is 1. The smallest x value is negative 1. And all the angles here or here will give me x values between negative 1 and 1. So if they give me x values between negative 1 and 1, cosine is, whenever I take the cosine of any angle, I will always get an answer between negative 1 and 1. So the range for cosine is also negative 1 to 1. So it's important to understand the domain for these functions and the range for these functions. You can plug any angle you want into sine and cosine. The only answers you will ever get from sine and cosine are answers between negative 1 and 1. You will never take the cosine of some angle and get an answer of, say, 2. That's impossible. It'll never happen because the answers for cosine will always have to be x-coordinates. In this case, the x-coordinates are only ones that are possible here are x-coordinates between negative 1 and 1. So that's just an important thing to understand with these functions. So now we know about the sine and the cosine function. We need to learn about the other 4 trigonometric functions, which isn't too bad since we already know the sine and cosine. So there are 4 more trigonometric functions. They are the tangent function, which we abbreviate TAN, the cotangent function, which we abbreviate COT, the secant function, which we abbreviate SEC, and the cosecant function, which we abbreviate CSC. So we define these in much the same way we do the sine and cosine, in that we look at where the terminal side of an angle hits the unit circle. So if an angle is in standard position and XY is a point of intersection of the terminal side of the angle and the unit circle, then the tangent, cotangent, secant, and cosecant function are defined as follows. The tangent of theta is equal to y over x, cotangent of theta equals x over y, secant of theta equals 1 over x, and cosecant of theta equals 1 over y. So we're basically using the same idea of looking at the point where the angle hits the unit circle, but rather than just look at the x or the y coordinate, we're really looking at either a combination of those 2 coordinates or 1 over the x or 1 over the y. The nice thing about this is there's not more points that you're going to have to learn. You know your unit circle points at this point, at least you should. And you're going to use those same points to develop the answers for these 4 trigonometric functions. Now there's one issue with this, is that these functions are all defined in terms of fractions. Well, if they're defined in terms of fractions, there's a problem when it comes to fractions, and that is that some fractions' denominators could end up being 0, and you don't want that. Well, look at this. Tangent has x in the denominator, secant has x in the denominator. If x is ever 0, if we're looking at a point, if we have a graph like this, and we have this unit circle, and we have our angle, theta, that angle hits a point, xy. If that x coordinate for this point is ever 0, then these 2 functions would have 0 in the denominator, and if they have 0 in the denominator, these would be undefined. It didn't happen with sine and cosine. Sine and cosine are never undefined because they're not defined by fractions. They're either just defined by solely the x or the y. But now these are y over x, 1 over x. If x is 0, tangent and secant are undefined. Same thing goes with y being 0. If y is 0, cotangent and cosecant are undefined. And that's something we're going to talk about in a little bit more detail in a couple seconds. All right. First, we can basically look at the tangent, the cotangent, the secant, and the cosecant in terms of sine and cosine. Remember, sine is equal to y and cosine of theta is equal to x. Well, if tangent of theta is equal to y over x, then I can really look at it as sine over cosine. Cotangent's x over y, so I can look at it as cosine over sine, so on and so on. Okay? So what happens is these new 4 trigonometric functions that we just talked about are really going to be defined in terms of the sine and cosine, and that's why knowing the sine and cosine already makes dealing with these a little bit easier. So here's our unit circle. You should have this unit circle down by now. You should know what the points are that go with which angles to be able to evaluate these trigonometric functions. So if I said find the tangent of pi 6, okay? Well, here's pi 6. Here's the point that goes along with pi 6. Since I know that tangent is y over x, tangent of pi 6 is going to be the y coordinate, which is 1/2, divided by the x coordinate, which is square root of 3 over 2. Well, if I'm dividing a fraction, I'd flip and multiply. The 2's cancel. I get 1 over the square root of 3. Normally we shouldn't have roots in the denominator, so you're probably not going to see the answer written that way in most cases. So then I'll rationalize this, multiply by square root of 3 over square root of 3, and I end up with square root of 3 over 3. So the tangent of pi 6 equals the square root of 3 over 3. How about let's do another one? How about we find the secant of 5 pi fourths? Okay. Well, if we look at this, secant is 1 over x. Here's 5 pi fourths. Here's the point that goes along with 5 pi fourths. So we're going to take this and say, well, this is 1 over negative square root of 2 over 2. Again, divide by a fraction, I get 1 times negative 2 over the square root of 2. So negative 2 over the square root of 2. I should then rationalize that. And I get negative 2 square root of 2 over 2. These 2's cancel, and I get negative square root of 2. So if you know your points, and you know how to define these 4 functions, you can do the same thing we've been doing all along now with these 4 functions. But here's what you got to watch out for. If I say find the cotangent of pi. Cotangent is defined by y over x. Here's pi. Here's x over y. Here's pi. Here's negative 1 over 0, negative 1, 0. And if I did that, negative 1 over 0, I get something that's undefined. Alright, that's fine. You can get an answer that's undefined. Well, what does that mean? It means that I can't take the cotangent of pi. Pi cannot be in the domain for this function because I don't get an answer out of it. So we'll have to discuss that about domains for these 4 trig functions. So you're going to see questions like this that say find the value for all the 6 trigonometric functions for each angle. So what this is asking you to do is to find the sine of pi thirds, the cosine of pi thirds, the tangent of pi thirds, the cosecant of pi thirds, the secant of pi thirds, and the cotangent of pi thirds. Alright. Now I write it down this way for a reason. These functions are all related. Okay? And the way I write my answer down can help me find my answer. So when I look at this, I go, okay, let's find sine and cosine first. So I think about my unit circle. Here's pi thirds. Here's my circle. And I gotta know what's that point. Okay? Well, that point is a half square root of 3 over 2. Okay? That's my point. So that means sine is square root of 3 over 2. And cosine is a half. And really what you're looking at is, this is the y coordinate. And this is the x coordinate. Right? Well, think about how these things are defined now. Tangent of theta is y over x. Well, if it's y over x and I know my y and my x, if I just take this value divided by this value, I'll get this value. And that's why I stack these up vertically like this, because once I find sine and cosine, I can get tangent out of that by doing sine divided by cosine gives me tangent. So if I look at that, I go, alright, well, if I take square root of 3 over 2 and divide it by a half, I have square root of 3 over 2 times 2 over 1. I cancel, and I get square root of 3. Alright, now I can do the same thing for these. There's a reason why I list cosecant across from sine, secant across from cosine, and cotangent across from tangent. Because if sine of theta equals y, cosecant of theta equals 1 over y. So the cosecant is the reciprocal of the sine. So if I know this answer here, to get this answer, I should just do the reciprocal. I should do 1 over y. So in that case, what I'm going to do is say, this answer is 2 over the square root of 3. And by writing it this way, I can clearly see that pattern. These are the reciprocals, and these you divide. Now, I'm not going to write my answer as 2 over square root of 3. I'm going to rationalize it. So I get 2 root 3 over 3, but still, there's my answer. Secant of pi thirds, that's the reciprocal of cosine. Cosine is a half, flip a half over, I get 2. Cotangent. Cotangent is reciprocal of tangent, because if this is y over x, this one is x over y. So I just take this thing and flip it over, so I get 1 over the square root of 3. Rationalize it, and I get the square root of 3 over 3. Let's erase some of this so you see it better. So here are my answers. Sine of pi thirds is square root of 3 over 2. Cosine of pi thirds is a half. Tangent of pi thirds is square root of 3. The cosecant of pi thirds is 2 square root of 3 over 3. Secant of pi thirds is 2. Cotangent of pi thirds is square root of 3 over 3. Okay? So oftentimes the way you write it down can make it easier for you to come up with all 6 of the answers. And once you know sine and cosine, you really got the other 4. So let's do another one. How about 135 degrees? So if I want to find the sine of 135 degrees, the cosine of 135 degrees, the tangent of 135 degrees, the cosecant of 135 degrees, the secant of 135, and the cotangent. Alright, so first I gotta do sine and cosine. Well, where's 135 degrees? So here's 135 degrees. What point am I looking at there on the unit circle? Well, that's going to be negative square root of 2 over 2 for the x and positive square root of 2 over 2 for the y. So sine's going to be square root of 2 over 2. Cosine's going to be negative square root of 2 over 2. And tangent is the y divided by the x. So if they're the same, just one's negative, I'll get negative 1. Alright. Cosecant. Cosecant's reciprocal of sine. So I'm going to just flip this over. 2 over the square root of 2. Rationalize it. And I end up with square root of 2. Same thing for the cosine, but it's the same, just negative. So negative square root of 2. And if I flip negative 1 over, I get -1. So here are my answers. Square root of 2 over 2, negative square root of 2 over 2. -1, square root of 2, negative square root of 2, -1. It's very fast to find these values if you set it up a certain way and you know your points. Up to this point, our primary focus has been looking at trigonometry through the unit circle. The unit circle is not the only way to do trigonometry, and what we're going to look at in this section is a more general approach to doing trigonometry, in that we can look at it using any circle. And then on top of that, we're also going to look at it using right triangles. And in a way, they kind of go hand in hand. But first, we're going to look at it just generally using any circle. So what happens is, since our circle doesn't have radius 1 anymore, our formulas for our trigonometric functions are going to have to change. Now, they don't change drastically, but they do change to the point where the radius is going to be very important. And I'll explain this in a second, but let's just look at the formulas. So if we said, let theta be an angle in standard position, okay, x and y be the point on the terminal side of theta, and r, which is your radius of your circle, which could always be calculated using this formula, the square root of x squared plus y squared, and that should never be equal to 0, then this is the way we can evaluate these trigonometric functions. Now this formula, r equals the square root of x squared plus y squared, this is the same thing as saying r squared equals x squared plus y squared. I just solve for r by taking the square root. R represents the radius of a circle, and any circle, whether the circle's radius 1, 2, 3, 4, 5. We look at the unit circle to this point, which was 1 equals x squared plus y squared. In that case, the radius was 1. But really, this can be used for any circle, so r could end up being anything, which would change this value here. Now, if we do this, this is what the formulas are going to have to be. The sine of theta is not going to just be y anymore. The sine of theta is going to be y over r, which is really the same formula as before. If you think about it, our formula was that sine of theta equals y, and for the unit circle, r was 1. So I could have wrote it as y over 1, which would be y over r, but we just said y, because y over 1 is just y. So this is really very similar to the formula we were using before, because now, since r is not 1, r could be anything, I have to then worry about dividing y by other numbers other than 1, which does make a big difference. Cosine is going to be x over r. Again, same reason. It was pretty much the same as the unit circle, which was just x, but now r is not going to be 1. Tan theta is going to be y over x, which is exactly the same. And the reason why that is, if you think about if I divide this by this, that's what we would do to get tangent, right? Sine divided by cosine gives me tangent. If I divide y over r and x over r, the r's cancel and I'm left with y over x. So it's the same thing, but since the r's are going to cancel out, you get the same answer. Cosecant is going to be the reciprocal of the sine, so if this is y over r, this is r over y. Same thing for secant, x over r, so this is r over x, and x over y reciprocal. Okay. Remember, we have these problems where these x's or y's can't be 0. Let me erase some of this so now you can see it again. You know, the domains, ranges, all that's still the same. The functions are still the same. The answers I should get for a common angle should still be the same. This is just a new way of looking at it when we don't have a unit circle. Let me draw you a little picture that sort of describes what's happening here. So here's your x and your y axis. What we would do is we would look at, say, a unit circle. Let's say this is a unit circle. It's not a great picture, but you know, this point right here would be 1, 0. This point right here would be 0, 1. And here's some angle theta, where the terminal side of this angle hits the unit circle. It's going to have an x and a y coordinate, right? These would be the x and y coordinates on the unit circle. I would use the x coordinate for cosine, the y coordinate for sine, and then x's or y's depending on which other functions I'm working with. Now if I don't have a unit circle, maybe I have a circle that's, say, out here and has a bigger radius. Well, if that circle has a bigger radius, then the terminal side of this angle is going to be hitting this point. It's still the same angle. Theta is still the same. I didn't change theta. I'm just extending the terminal side out far enough so that it hits this bigger circle. That bigger circle is going to have a completely different x and y. So let's label this, I don't know, x1, y1. Okay? But this x and this x here are not the same, clearly. They're in totally different locations. Same thing with the y's. Now what I can't do, if I want to find, say, the cosine of theta, I can't just look at this x-coordinate, because that's going to give me a different answer than this x-coordinate. I can only look at the x-coordinate if I'm in the unit circle. If I'm not in the unit circle, then I can't just look at the x-coordinate here and say this x-coordinate is going to be the cosine of theta. But what I can do is look at this distance here. This distance here is r. And what happens is if I take x1 and divide it by r, that will give me the same thing as this x-coordinate here. Because circles are proportionate. All circles are proportionate, and the points are proportionate based off of the radius. Well, if the points are proportionate based off the radius, this x-coordinate and this x-coordinate are related in terms of that they're related based off of this distance. So if I divide this x-coordinate by the radius, what it does is essentially takes this x-coordinate and brings it back to that x-coordinate. And that's why I have to do x over r, or same thing for the y over r. I have to bring this y-coordinate back to the unit circle, and I do that by dividing by the radius. And this radius can be found by doing the square root of x squared plus y squared. If I know these 2 points, these 2 coordinates for the points, I can figure out what r is, and then I can use that to divide my x and my y coordinates to get back to my unit circle. And that way, when I take the cosine of theta, I'll always get the same answer, regardless of whether or not it's a unit circle or any radius circle. That goes the same for, say, a smaller circle, right? The point here is still going to be different. If I divide that point by this distance here, r, then that point divided by r will get me back to this point. So these are the new formulas you're going to have to work off of. And I think the biggest thing that you're going to have to deal with here is to assume for all problems from here on out that you are not working with a unit circle. That way, if you are working with a unit circle, you would just find out that r is 1, and you plug 1 in here for r, and you would get the right answer. But if it's not a unit circle, then you're still covered because you're still dividing by whatever r is, and you're using these formulas. So from this point on, assume that you're not working with a unit circle, and you can't just say sine of theta is equal to y, cosine of theta is equal to x, and so on. You have to think about it in these new formulas. That sine of theta equals y over r, cosine of theta equals x over r, etc. So here's your typical question that you would see for these types of problems. Let 4, -3 be on the terminal side of theta. Find the values of the sine, the cosine, and the tangent of theta. So what I would do is I would draw a picture first. So I'm looking at this very simple picture. Okay. 4, -3 is right here. Okay. This point is on the terminal side of theta. So let's just say here's theta. That doesn't matter whether I go clockwise or counterclockwise. I end up here. This is theta. This is the terminal side. And this point's on the terminal side. What you can think of is that there's some circle for which this point lies on, which is also on the terminal side. This is the intersection point. So now what I want to do is I want to find what the sine of theta, the cosine of theta, and what the tangent of theta are. Well, I need y over r for sine, x over r for cosine, and y over x for tangent. And I use these formulas because I gotta assume that this distance right here is not 1. This is my r. I don't know if it's 1 or not. There's no way of knowing unless I calculate it. So if I assume it's not 1, I'm covered whether it is or isn't. So let's figure out what r is first. R is going to be the square root of x squared plus y squared. So I'm going to get the square root of 4 squared plus negative 3 squared. So the square root of 16 plus 9, so 5. Square root of 25 is 5. So if r equals 5, I know that x equals 4 and y equals negative 3. That tells me that sine is going to be negative 3 over 5. Cosine is going to be 4 over 5. And tangent is going to be negative 3 over 4. So I just found the values for these three functions for this particular angle. I don't know what theta is, but I do know what point theta relates to, and it's not even necessarily on a unit circle, because the radius of this circle is 5. But it doesn't matter. I don't have to have a unit circle. As long as I know a point on the terminal side of the angle, any point, I have this point, this point, this point, any point on this terminal side, I can use that point to help me calculate the sine, the cosine, and the tangent of theta, even if I don't know what theta is. Now, if I wanted to know what theta was, there's a way to find that out. Let's just look at that real quick. I mean, it's not really something that's required right now. We'll do it later in the section, but while we're here, we might as well. So if I want to know what theta is, I just need one of these values to do it. So let's look at sine. I know that the sine of theta equals negative 3/5. So if I want to find what theta is, well, remember, the sine of theta equals some number. I'm trying to figure out what theta is. That is the same thing as this question. The arcsine of negative 3/5 equals theta. Remember, this function is the function that goes backwards. It says if I have the answer for a sine, I can go back and figure out what the angle is. So this arcsine function can help me figure out what theta is because I know what the sine of theta is. Now here's the problem. You'd have to use a calculator in order to do this because negative 3/5 is not a common answer we're used to getting for some sine of theta. Common answers we're used to getting here would be like 1/2, square root of 2 over 2, square root of 3 over 2, 0, 1, negative 1. Right, these would be common answers for common angles. Like we would have 30 degrees, 45 degrees, 60 degrees, 90 degrees, whatever. So this, whatever angle this is, it's not a common angle that's giving me this answer. But this still doesn't mean I can't find the angle. So this is where you would want to use your calculator. You'd want to find the arcsine of negative 3/5 in your calculator. Your calculator has a button that looks like this. And usually right above that button you see this. That's your inverse sine, your arcsine. Usually you have to hit the second command to get to that. So every calculator is a little different. I can't really necessarily tell you exactly how to do it on your calculator. Sometimes what you'd have to do is you'd have to hit this button first. Something like this would pop up. And then you'll put the negative 3/5 into that. Hit the equal sign and be done. Some calculators you have to hit the negative 3/5 in first. Then you hit that button. Every calculator is a little different. But if I was going to do this for this particular one, I would find out that theta equals negative 36.9 degrees. Let me double. Yeah, so negative 36.9 degrees. So try this in your calculator. See if you can come up with this answer. But, I mean, it doesn't relate to this problem particularly. For this problem, you would just stop here. But if you wanted to know what theta is, we can use this point to figure out what theta is as well. Not just to figure out what the sine, cosine, and tangent of theta are, but what the angle is itself. Just by knowing this little bit of information. Here's another problem. Different information, but same kind of problem in that what you want to do is find the sine of some angle. So I find the sine of theta. We don't know what theta is, but we got some information about it. So what they told us is that the cosine of theta equals 3/5. Okay? And the tan of theta is negative, less than 0. What I would like to do with most of these is I like to draw a picture. So cosine is positive and tangent is negative. So if I think about where that is, well, cosine's positive and tangent's positive in quadrant 1. In quadrant 2, cosine's negative and tangent is negative. In quadrant 3, cosine is negative and tangent is positive. And in quadrant 4, cosine is positive and tangent is negative. And I'm doing that by just looking at the x's and y's. X's are positive here and negative here and here. Tangent is y over x. So if tangent is y over x and x's and y's are both positive, I get a positive. X's and y's are different, so I get a negative. X's and y's are the same, both negative, so I get a positive. And they're different, so I get a negative. So this is the quadrant that my angle is going to fall into. This is theta. Okay? So right now, if that's theta, I got to think sine. Sine in quadrant 4 is negative. So I know I'm going to get a negative answer for this. Now I got to come up with my actual answer. Well, let's look at this. Cosine of theta is 3 over 5. I could calculate that by doing x over r, right? That's how I find the cosine of theta. So whatever theta was, when I took the cosine of it, if I took the x coordinate divided by the r, I would get 3/5. So let's just say x is 3 and r is 5. If x equals 3 and r equals 5, then the cosine of theta would give me 3/5. Alright, well, what do I need for the sine of theta? The sine of theta, I need y over r. Well, if I already have r, that's 5. All I need to do is figure out what y is. Well, that's where this equation is going to come in again. X squared equals, scratch that. R squared equals x squared plus y squared. This equation is an important equation in that it relates the 3 variables that you need to do every one of these problems. In that sine, cosine, tangent, cosecant, secant, and cotangent are all defined in terms of these 3 variables. Now, they only need 2 out of the 3, but they all, in the end, need these 3 variables somehow. Sine needs y and r, cosine needs x and r, etc. So this equation right here tells you how these 3 variables, x, y, and r, relate. Well, here I know what x and r are, and I need to find y. Well, r is 5, so 5 squared. X is 3, 3 squared. Now I need to find y. So just solve this equation for y, and you got your answer. If you do that, you get y squared equals 25 minus 9. So y equals plus or minus the square root of 16. So plus or minus 4. You get 2 answers. But we know that sine would have to be negative. You get 2 answers because cosine is positive in 2 different locations, and that's what I'm using to find this, right? The cosine being the 3/5. Cosine's positive in 2 locations. If you think about it, sine is positive in one of them and negative in the other, and that's why we get the 2 different y values. Anyway, y is going to be negative 4 because we know we wanted the negative, so if sine of theta equals y over r, y was negative 4, then sine of theta is negative 4/5. And that's really why we need this piece. This piece tells us where my angle is going to be. If I know that cosine is 3/5, well, that means my angle could be here or here. Both of these would give me a positive answer for cosine. Knowing that tangent's also negative eliminated this one and made me focus down here, which also helped me figure out that my sine would have to be negative. So, depending on what information you're given in the problem, you're going to have to evaluate some trigonometric function. The idea is you have these 3 variables, x, y, and r. Somehow in the problem, you're going to be given 2 out of the 3 of these, and you're going to have to find the 3rd. And this equation right here oftentimes will help you do that. The trick is figuring out which 2 the problem gave you, and then finding the other one. So here you were given x and r, and you need to find y. If I back up to this problem, here you were given x and y, and you had to find r. No matter what you're given, you got to be given 2 out of the 3 variables, and if you're given 2 out of 3 variables, you can find any of these trigonometric functions. This equation is important. Whether you write it as this way or you write it this way, it's the same thing. R is the radius of a circle, and the key thing for R is that R should always be positive. R can't be 0, and R is not going to be negative, because R is this distance here. So if you ever find R to be negative, then you messed up somewhere. Now that we've gone through the whole circle approach to doing trigonometry, we can then discuss sort of the last approach, which is using right triangles. This is actually more of the same of kind of what we've been doing. If you think back to how we started coming up with the points on the unit circle, like the square root of 2 over 2 and the square root of 3 over 2 and the 1/2, where those points were coming to, we did some geometry to try and get there, and what we really did was we started to draw right triangles. And that's essentially the idea of what this is, but we're sort of pulling the right triangles out of the circle and not looking at it as a circle anymore, but more of a triangle. The major difference is, when you do a circle, you relate a point on the circle, which is that point of intersection. This point is related to this angle, and that's what the trigonometric functions are doing. They're relating points to angles. So cosine of theta is relating the x-coordinate to theta, or if we use our new definition, x over r to theta. Cosine is relating y over r to theta, etc. The right triangle approach is we're not going to be relating points to angles, but we're going to be relating sides of the triangle to angles. So it's just a different way of thinking about things. But in the long run, it's a lot of the same stuff. So, just to be familiar with some terminology, alright, a right triangle is a triangle that has a 90-degree angle inside of it. So that angle right there is a 90-degree angle. And what we need to do is we need to look at the sides of the triangle. We would label those sides hypotenuse, opposite, and adjacent. And the way you label them is dependent on which angle in the circle or in the triangle you're talking about. This triangle has 2 angles in it, or 3 angles in it, 2 of which are not the 90-degree angle. So you have your 90-degree angle, then you have this angle here, which we'll call, say, beta, and this angle here, which we could call theta. So if we look at these 2 angles, right, let's look at theta. So if we're looking at theta, for theta, this side of the triangle will be considered the hypotenuse, which we'll label HYP. The hypotenuse is the side that connects the angle that we're looking at, theta, and the other non-right angle, in this case beta. It's the side that doesn't touch the 90-degree angle. So we call that the side sort of opposite the 90-degree angle, the hypotenuse. For theta, and even for beta, this will be the hypotenuse. Now, opposite and adjacent is where things can change. So, if I look at this here, this side right here, we're going to call the adjacent side, which I'll label ADJ. This is the side that connects theta to the right angle. So this would be the adjacent side to beta, or to theta. Okay? And this would be considered the opposite side to theta. Okay? In that this is the side that connects the right angle and the other non-right angle. It's the side that doesn't touch theta. Now if I'm looking at beta, the hypotenuse is still the same hypotenuse. This is the side that touches the 2 angles that aren't right angles, the side opposite the 90-degree angle. But this side here is going to be considered the adjacent side to beta. This is the side that touches my angle, beta, and the 90-degree angle, connects those 2. And this would be considered the opposite side to beta. It's the side that doesn't touch beta. So when I refer to this side right here, I need to figure out which angle am I referring to this side in terms of. If I'm referring to this side in terms of theta, this would be called the adjacent side. If I'm referring to this side in terms of beta, this would be the opposite side in terms of beta. What you need to know also as part of this is not just the terminology, but everyone should know the Pythagorean Theorem, that a squared plus b squared equals c squared. Typically what we'll say is that this side is a, this side is b, this side is c. So a squared plus, it doesn't matter, a squared plus b squared equals c squared. This side length squared plus this side length squared equals this side length squared. Now which one of these you call a and b doesn't really matter, because it's a squared plus b squared. Since you're adding them, the order can be switched around, but which one is c? C is always the hypotenuse. That's important. A and b are the legs, what we'd say the legs of the triangle, and c is the hypotenuse. Which you can look at this as the opposite squared plus adjacent squared equals hypotenuse squared. Which one you call opposite and adjacent can be reversed depending on what angle you're talking about, but still opposite squared plus adjacent squared should equal hypotenuse squared, should be the consistent one. And once you get that down, then what we can do is look at using these side lengths to define our trigonometric functions. So if I look at a right triangle, and I say this angle right here is my theta, this is my hypotenuse, this is my opposite side, this is my adjacent side. So what I'm going to do is I'm going to define the sine of theta to be the opposite side divided by the hypotenuse. The cosine of theta will be the adjacent side divided by the hypotenuse. The tangent of theta will be the opposite over the adjacent, which I could calculate by doing this one divided by this one gives me this one, because the hypotenuse would cancel and I have opposite divided by adjacent. These three here are the reciprocals. Still, I mean, everything we've talked about so far still has to stand, even if we're looking at right triangles. So the reciprocals, the division, all that's the same. We're just using the sides of the triangle instead of x's and y's and r's. Now this is really the same thing that we've been doing, because if I now relate this to the circle, here's my circle, here's my angle, theta, here's this point, x, y. Well, if I make a right triangle inside this circle, okay, this right triangle would have this be my hypotenuse, which was the same thing as what we called r. This side length is based off of whatever this y coordinate is. So the y coordinate is the length of this side, and the x coordinate is the length of this side. So whatever this point is, that's going to tell me the lengths of the sides of this triangle. So if I think about this, we said that sine of theta equals y over r. But if you look at this, y is actually opposite and r is adjacent. So that's the same thing as opposite over hypotenuse, which is the same definition I have here. So it all links together. It's just a matter of whether or not do you want to look at a circle, do you want to look at a triangle. I think lots of times what you're going to do is a combination of both, like this picture has in here. I have a triangle inside my circle, but this is how we can use right triangles to evaluate trigonometric functions. So here you need to be familiar with these definitions. Now, if you've had any type of trigonometry before, or maybe you've just heard some phrases from trigonometry, you might have heard something called Sohcahtoa. I'm not a huge fan of a lot of these sayings that you use to memorize some of these terms, but it is something that is used quite often, so I should mention it. So you hear this term Sohcahtoa. So it's this. So if you sound that out, Sohcahtoa. What it means is that sine is opposite over hypotenuse. That's the S, the O, and the H. Cosine Come on. Cosine is adjacent over hypotenuse. So that's the A and the H. Okay. And tangent is opposite over adjacent. So that's tangent, opposite, adjacent. So when you see this Sohcahtoa, again, let me write it clearer. Sohcahtoa. It helps you remember sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent's opposite over adjacent. Like I said, I'm not a big fan of these sayings, but if you are, and if you think that helps to help you memorize these, then go ahead and use it. Now we've looked at special angles to help us find the sine and cosine tangent of these special angles in the unit circle. Well, rather than look at them as a unit circle, we can look at special triangles with these special angles in them to help us do some of the basic trigonometry we've done so far. So there's two special triangles you need to make yourself familiar with. They're both right triangles. And then this triangle right here would be my 30 degrees, my 60 degrees, and my 90 degree triangle. These are two of my special angles. So if I look at this triangle, the sides of this triangle would be square root of 3 here, 1 here, 2 here. The side opposite the 60 degrees is square root of 3. The side opposite the 30 degrees is 1, and the hypotenuse is 2. Another one would be this 45, 45, 90 triangle. In that case, I'd have 1, 1, square root of 2. Now, where these numbers come from, it's some geometry, it's a little bit of Pythagorean Theorem, and we've actually done this already when we were coming up with the points around the unit circle. These were the triangles really we were using for the most part. Now, these triangles can help you find things like the sine of 30 degrees. You should already know what the sine of 30 degrees is based off of all the stuff we've done so far, but you can also use these triangles to help you do the sine of 30 degrees. So sine is my opposite over hypotenuse. Well, if it's opposite over hypotenuse, here's 30 degrees. This would be considered the opposite side. This would be considered the hypotenuse. So sine of 30 degrees should be 1 over 2 or a half, which would get the same thing as if you look at the unit circle, but this is just another way of coming up with that answer. And basically what I tell students is, what would you rather do? Would you rather remember these two triangles or the entire unit circle? And I think most times students would say they'd rather remember these two triangles. But for us, at this point, you already know the entire unit circle, so it doesn't matter. What I can do is just take these two triangles and place them around the circle over and over and over again to start creating the points around the unit circle that I'm going to come up with. But any way you do it, you should be able to find the sine of 30 degrees, or let's say the cosine of 45 degrees. Cosine would be adjacent over hypotenuse. So here's my 45 degree angle. This would be the adjacent side to that. This would be the hypotenuse. So this is adjacent, this is hypotenuse. So I do 1 over the square root of 2. If I rationalize that, I get square root of 2 over 2. So here's the kind of question that you might see as it relates to triangles, right triangles specifically. It's going to say, solve the right triangle. In that case, they're going to give you pieces of the triangle. Now, how you label the triangle really doesn't typically matter. This is how you're going to see the most triangles labeled. The sides of the triangle will be labeled as lowercase letters, and the angles inside will either be Greek letters or capital letters. So we're going to do the capital letters. So what I'm going to do is this. I'm going to label two of the sides A and B. The hypotenuse is always going to be C. So whatever side I call A doesn't matter. I'll say this side is A, this side is B, this side is C. And then the angles inside the triangle typically are labeled with the opposite side's letter but as a capital. So this will label capital A and this will label capital B, because that angle is opposite that side, that angle is opposite that side, and they should have the same letters. If you don't want to use capital letters, what you also might see is the Greek letters. You might see beta and alpha. But this is your typical setup for a right triangle. So they gave us A to be 10 and C to be 12, and it says solve the right triangle. When you're solving the right triangle, what you got to do is find the remaining pieces. So beta, alpha, and B. The first thing we're going to find is side B. There's a couple of things you need to know. One is that A squared plus B squared equals C squared. So A is 10, B we don't know, and C is 12. So that tells me that B squared equals 144 minus 100. So B equals the square root of 44. Now I'm going to use the positive square root. Whenever you're talking about sides of a triangle, your values should always be positive. You know, normally when you take the square root, you should do plus and minus. But since we're just talking about triangles themselves, sides of triangles are always positive. So I'm just going to say plus. I would simplify the square root of 44 as the square root of 4 times 11, which is 2 square root of 11. So B is 2 square root of 11. So now I have two more parts to find, angle A and angle B, or alpha and beta, whichever you want to call them. So let's find alpha. So if we want to find alpha, what do we need to know? We need to know what that angle is. There's a couple of things I can do. I can use the sides of the triangle to help me do this. Now, if I have a choice, I want to pick two out of these three sides. I probably would want to use this one and this one. Just for number's sake, those two numbers are easier than this number is right here. So if I'm going to look at these two numbers here, I gotta think, okay, here's my angle. This is the opposite side for alpha, and this is the hypotenuse for alpha. Okay. What trigonometric function do I use in terms of opposite and hypotenuse? And that would be sine. Sine of alpha is opposite over hypotenuse. Well, if that's the case, then the sine of alpha is equal to 10 over 12, or 5/6. Well, here's a question that we were just looked at a little while ago. If I know that the sine of alpha is 5/6, how do I find my angle alpha? Well, the arc sine of 5/6 should give me alpha. Again, if I plug that into my calculator, because 5/6 is not an answer I'm used to using when it comes to certain trigonometric angles, I would get 56.4 degrees. So now that I know that this is 56.4 degrees, I need to find beta. Well, there's two ways I can do it. I can use the same approach to find beta that I used for alpha, or if I know that the sum of angles inside any triangle equals 180 degrees, then I know that alpha, or A, plus B has to equal 90 degrees. Because I already know that one of them is 90. So if I know that A is 56.4, then beta is going to be 90 minus 56.4. In that case, beta equals 33.6 degrees. So now we solved the whole triangle. We know what all the sides are. A is 10, C is 12, B we found to be 2 square root of 11. And we know what all the angles are. One of them is 90 degrees because it's a right triangle. One of the angles, alpha, is 56.4. The other angle, beta, is 33.6. So this is a fairly common type of question when it comes to right triangles, is this solve the triangle. Essentially what it means is, given a certain amount of information, find the remaining parts. So find the remaining angles and the remaining sides. Another common questions that you can come up with right triangles are some application questions. And a lot of these have to do with applications of, say, surveying. Surveying is a way of calculating large distances using angles, and that's really kind of what this is all about. So for this question, if the sun is 30 degrees up from the horizon and shining on a tree forming a 50-foot shadow, how tall is the tree? With all this, it's sometimes helpful to draw a little picture. You don't have to be an expert, artist to do this. So you have, your sun. Now you have your tree. Right, it's shining down on the tree. If it says it's 30 degrees up on the horizon, that means this angle right here is 30 degrees. The shadow is this length right here. Right, that's a 50-foot shadow. And what you're looking at really is a right triangle. So if I look at this right triangle right here, okay, I know that this angle is 30 degrees. I know that this side is my 50 feet. And the question is, how tall is the tree? Well, this distance here is the height of the tree. So I'm trying to find out this distance, which I'll call h. So if I look at this triangle, again, redraw it so you can see it better. I get 30 degrees, 50, and h. I need to find h. Well, think about this. If this is a right triangle, these two sides in relationship to this angle are the opposite side and the adjacent side. Well, if I look at tangent of theta is opposite over adjacent. So the tan of 30 degrees should be equal to the opposite side, which is h, over the adjacent side, which is 50 feet. Well, if I need to find h, let me solve this equation for h. I'll multiply by 50 feet on the other side. I get 50 feet times the tan of 30 degrees equals h. And that's my solution. Now, you probably could do better than that. 50 times tan of 30. Well, tan of 30 degrees is going to give you, what, square root of 3 over 3. And I can say that's how tall the tree is. This is going to be in feet still. Even that's probably not great though, because if I told you this is how tall a tree is, you would really have no idea how tall that tree is. So I think your next best bet is to then say, okay, well, yeah, that's the exact value for how tall the tree is, but let me plug this in my calculator, and I'm going to get an estimate for how tall the tree is. And we use these squiggly equal signs, I guess you would call them, to denote that this is not actually what h equals, but this is an estimate for what h equals. And this is probably your better answer for this question, even though in most questions getting the exact answer is the best. For this question, it would make most sense to get this answer in decimal form, which would really have to be rounding, so it would be an estimate. So you're looking at a height of about 28.9 feet. Okay? And if I said the tree is 28.9 feet tall, that number probably would make the most sense to you. Even though this is the exact height of the tree, probably the better answer mathematically, in everyday terms, this is probably your better answer. Let's do another one. So if a rope is tied to the top of a flagpole, it's 30 feet long, then what angle is formed by the rope and the ground when the rope is pulled to the ground 25 feet from the base of the pole? So again, draw a little simple picture. Here's your flag. Okay. You have a rope at the top of the flagpole tied to the ground. What you got is a right triangle. You know the rope is 35 feet long. You know that it's pulled 25 feet from the base, so that's this distance. and they want to know what this angle is. Let's call that theta. Well, as far as theta goes, this would be the adjacent side. This would be the hypotenuse. So that would be cosine is adjacent over hypotenuse. So the cosine of theta equals 25 over 35, or simply 5 over 7. The question said, what's theta? What's the angle? Well, if I want to find theta, this is where inverses come up. Theta can be the arc cosine of 5/7. And while that is the exact value for theta, that does not give you an idea of what angle theta is. So what you're probably going to want to do is plug this into your calculator, which you're going to just then have to write a decimal version, which would then be an estimate, because you're going to round that decimal, and the arc cosine of 5/7 is 44.4 degrees. Okay? For most problems, I want you to give me the exact answer, especially if it says find the exact value. For these word problems, however, I am perfectly fine with you giving me an estimated answer, because that's a more realistic answer that would make most sense to you. If I said the angle is 44.4 degrees, roughly that's 45 degrees, you would have a visualization in your brain as to how big or how small that angle is. If I said that angle is the arc cosine of 5/7 degrees big, you really probably have absolutely no visualization as to how big or how small that angle is. So in realistic terms, this is probably the better answer. In mathematical terms, this is the better answer. In most questions, I want the exact answer, especially when I say find the exact answer. But in these word problems, again, the best answer you can give usually is the estimated answer, and I'm fine with that.